Introduction to Merkle Trees. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving into one of the most fundamental data structures in blockchain technology, the Merkle tree. You might be wondering what makes Merkle trees so special. They are the secret sauce that allows blockchains to efficiently verify massive amounts of transaction data without having to process everything. Think of it like this. If blockchain is a massive library with millions of books, a Merkle tree is the clever cataloging system that lets you verify any single book belongs to that library without checking every shelf. This presentation will break down how Merkle trees work, using simple analogies, visual diagrams, and step-by-step examples that anyone can understand, even if you have never touched blockchain technology before. The problem: verifying transaction data. Before we understand Merkle trees, let's understand the problem they solve. Imagine you have a blockchain block containing thousands of transactions. Every time someone wants to verify that a specific transaction is included in that block, do they really need to download and check all thousands of transactions? That would be incredibly inefficient and slow. In early systems, this was exactly the problem. Verifying one transaction meant processing everything. It's like having to read an entire encyclopedia just to verify one fact is in there. This scalability issue could have killed blockchain before it even started. We needed a way to prove a transaction exists in a block without having to examine every single transaction. This is where Merkle trees come in as an elegant solution. What is a Merkle tree? A Merkle tree is a special data structure that organizes information in a tree-like hierarchy where each piece of data is connected through cryptographic hashes. Here's a simple way to think about it. Imagine you have a bunch of Lego receipts showing who bought what. Each receipt gets turned into a unique code, like a digital fingerprint. Then you start pairing these codes together. Receipt 1 plus Receipt 2 creates a new combined code. Receipt 3 plus Receipt 4 creates another combined code, and so on. You keep combining these codes in pairs, moving up the tree, until you have just one final code at the very top. That's called the Merkle root. This root represents every single transaction below it. The beauty is that if anyone changes even one letter in any transaction at the bottom, the entire Merkle root at the top changes completely. This makes the tree incredibly secure and tamper-proof. Building a Merkle tree. Step by step. Let's walk through exactly how a Merkle tree is constructed, step by step. First, you start with your transactions at the bottom. These are called leaf nodes or leaves. Each transaction gets hashed using a cryptographic hash function, turning it into a fixed-length string of characters. So transaction T1 becomes hash H1, transaction T2 becomes hash H2, and so on. Once you have all your leaf hashes, you pair them up. For example, take H1 and H2, combine them together, and hash that combination to create H12. Take H3 and H4, combine and hash them to create H34. You continue this pairing and hashing process for every pair at that level. Then you take those results and pair them up again. H12 and H34 get combined and hashed to create H1234, and so forth. You keep climbing the tree, having the number of hashes at each level, until only one hash remains at the very top, the Merkle root. This root is stored in the block header and represents a cryptographic summary of all transactions in the block. The power of pairing. How siblings work. One of the most important concepts in Merkle trees is the sibling relationship. At every level of the tree, each hash has exactly one partner, its sibling. At the leaf level, transaction T1 is paired with transaction T2, so T2 is T1's sibling. Similarly, T3 and T4 are siblings. When we move up to the next level, H12 and H34 become siblings because they're paired together to create the next level hash. This sibling pairing continues all the way up the tree. What if you have an odd number of transactions? Great question. If there are 5 transactions, the last one simply pairs with itself, so T5 gets hashed with T5 to create its parent hash. This keeps the tree structure balanced and consistent. The sibling relationship is crucial because when you want to verify that a transaction is in the tree, you only need to know the sibling hashes along the path from your transaction to the root. You don't need every hash in the tree, just the ones that pair with yours at each level. Merkle tree verification. The magic. Now, we get to the real magic of Merkle trees. Verification. Let's say you want to prove that your transaction, T3, is included in a block containing 8 transactions. Do you need all 8 transactions? No, you don't. You only need 3 pieces of information: the sibling hashes along your path to the root. Here's how it works. You already have H3, the hash of your transaction. You ask for H4, which is H3's sibling at the leaf level. You combine H3 and H4 and hash them to get H34. Now you need H12, which is H34's sibling at the next level. You combine H34 and H12 and hash them to get H1234. Finally, you need H5678, which is H1234's sibling at the next level. You combine H1234 and H5678 and hash them to get the root. Now you compare your calculated root with the official Merkle root stored in the block header. If they match perfectly, you have proven your transaction is in the block. If they do not match, something is wrong. Either the transaction was not included, or someone tampered with the data. Why verification is so efficient? The efficiency of Merkle tree verification is where things get really impressive. At first, you might think, wait, I still need to hash my way up the tree level by level, isn't that a lot of work? Actually, it's incredibly efficient, and here's why. The key is that you only need 1 sibling hash per level, not every hash at that level. If your block has 8 transactions, that's 3 levels above the leaves, so you need only 3 sibling hashes. But here's where it gets amazing. If your block has 1 million transactions, the tree only has about 20 levels because the tree height grows logarithmically. That means you only need about 20 hashes to verify your transaction among 1 million transactions. That's the power of logarithmic scaling. Each time you double the number of transactions, you only add 1 more level to the tree. So verification remains lightning fast even as blocks contain more and more data. A Merkle proof is typically just a few hundred bytes, even for blocks with thousands of transactions. Understanding tree height and capacity. Let's talk about how Merkle trees scale with the number of transactions. The height of the tree refers to how many levels of hashing occur above the leaf level. With 4 transactions, you get 2 levels of combining. First, the 4 leaves pair into 2 hashes, then those 2 pair into the root. With 8 transactions, you get 3 levels. The pattern is mathematical. The maximum number of transactions you can fit equals 2 raised to the power of the height. A tree of height 10 can handle 1024 transactions. A tree of height 20 can handle over 1 million transactions. A tree of height 30 could theoretically handle over 1 billion transactions. Each level you add doubles the capacity, but verification only requires 1 additional hash operation. In real blockchain implementations like Bitcoin, blocks typically contain a few thousand transactions, requiring a tree depth of only 12 to 14 levels. The verification remains incredibly fast because of this logarithmic relationship between tree size and verification cost. Transaction ordering and pairing. An important question that often comes up is, how does the system decide which transactions get paired together? The answer is beautifully simple. Transactions are paired based on their order in the block. There is no randomness or complex algorithm. If your block contains transactions T1 through T8, then T1 pairs with T2, T3 pairs with T4, T5 pairs with T6, and T7 pairs with T8. The pairing happens strictly left to right in the order transactions appear. This deterministic ordering is actually a crucial security feature. The Merkle root does not just represent the content of transactions, it also represents their exact order. If a malicious actor tried to swap the positions of two transactions, even if the transactions themselves were not modified, the hash pairings would change completely. This means the new Merkle root would be different, and the tampering would be immediately detected. The block header stores this Merkle root, and any change to transaction order or content will fail verification. Block capacity and system limits. A common misconception is that Merkle trees limit how many transactions can be in the blockchain system. This isn't true. The Merkle tree itself has no hard limit. It can grow as tall as needed to accommodate any number of transactions. The real limit comes from the block size, which is set by the blockchain protocol rules. For example, Bitcoin limits blocks to around 1 to 4 megabytes, which typically holds 2,000 to 4,000 transactions. Ethereum uses a gas limit instead of a size limit, restricting blocks based on computational complexity rather than raw size. Once a block reaches its limit, it gets sealed with its Merkle root and added to the chain. Then a new block starts with a fresh Merkle tree. Across the entire blockchain, you can have billions of transactions. They're just divided among many blocks, each with its own independent Merkle tree. Think of each Merkle tree as a filing cabinet for one folder, and the blockchain as the entire filing room with unlimited folders. The mempool and transaction selection. Before transactions make it into a block, they live in a waiting area called the memory pool. Whenever you send a transaction, for example, if Alice sends Bitcoin to Bob, that transaction is broadcast to the entire network and resides in every node's memory pool, awaiting inclusion in a block. Miners examine this memory pool and decide which transactions should be included in the next block they are building. How do they decide? The primary factor is the transaction fee. Transactions that pay higher fees are more profitable for miners, so they are typically selected first. This creates a fee market where users can pay more to receive faster confirmation. Miners also consider block size limits. They continue adding transactions until the block is full. They must validate that each transaction is legitimate, verifying proper digital signatures, absence of double spending attempts, sufficient funds, and so forth. The miner arranges these selected transactions, builds the Merkle tree using them, and includes the Merkle root in the block header before mining begins. Distributed consensus. No central directory. One of the most fascinating aspects of blockchain is that there is no central directory or master list tracking which transactions are in which blocks. Bitcoin has no company, no server, no authority keeping an index. Instead, every full node in the network maintains a complete copy of the entire blockchain. Each node knows all the blocks, their order by height, and all transactions inside each block. They achieve agreement through consensus rules that every node follows. When a miner creates a new block, they broadcast it to the network. Every other node validates it, checking that transactions are valid, the proof of work is correct, and it properly references the previous block. If the block passes all checks, nodes add it to their local copy of the blockchain. The block itself contains everything needed: the list of transactions, the Merkle root, and a hash pointer to the previous block. This creates an unbreakable chain where each block links to its predecessor. If someone tried to modify an old block, the hash links would break, and the entire network would reject it. Preventing double spending with UTXOs. Let's address an important question. What if someone tries to send the same payment twice? Wouldn't duplicate transactions have the same hash? This is where Bitcoin's UTXO model comes in. UTXO stands for Unspent Transaction Output. Bitcoin doesn't track account balances like a bank. Instead, it tracks individual chunks of Bitcoin that haven't been spent yet. Every transaction has inputs that consume previous UTXO and outputs that create new UTXO. When you spend Bitcoin, you are actually consuming specific previous outputs and creating new ones. Each input can only be used once, ever. If you try to create a second transaction spending the same input, every node will reject it as a double spend. Even if two payments look identical, for example, the same amount and the same recipient, they will have different inputs, different signatures, and therefore completely different transaction hashes. The transaction hash is calculated from all the binary data, including inputs, outputs, signatures, and metadata. Change even a single bit, and the hash is completely different. This ensures every transaction is cryptographically unique and prevents any double spending attempts. Real-world example. Verifying a transaction. Let's walk through a complete real-world example of Merkle tree verification. Imagine we have a block with 8 transactions: Alice, Bob, Carol, Dave, Eve, Frank, Grace, and Henry each made a purchase. Carol wants to prove her transaction is in the block. First, Carol's transaction gets hashed to create H3. She needs to climb the tree to the root. At the leaf level, her sibling is Dave's transaction, hash H4. She combines H3 and H4 and hashes them to get H34. Moving up one level, H34 needs a sibling. That's H12, which represents Alice and Bob's combined hash. Carol combines H34 and H12, and hashes them to create H1234. Moving up again, H1234 needs its sibling. That's H5678, representing Eve, Frank, Grace, and Henry combined. Carol combines H1234 and H5678 and hashes them to produce the Merkle root. She compares this root to the official Merkle root stored in the block header. They match perfectly, proving Carol's transaction is legitimately included in this block. The entire proof only required 3 sibling hashes, H4, H12, and H5678. She didn't need to download or process any other transactions. Security through cryptographic hashing. The security of Merkle trees comes from the properties of cryptographic hash functions. These functions have several critical characteristics. First, they are deterministic. The same input always produces the same output. Second, they are quick to compute but impossible to reverse. You cannot figure out the input from the output. Third, they are collision resistant. It is virtually impossible to find 2 different inputs that produce the same hash. Fourth, they have the avalanche effect. Changing even 1 bit of input completely changes the output. This last property is what makes Merkle trees so tamper-proof. If someone tries to modify a single transaction at the leaf level, that transaction's hash changes. This causes its parent hash to change, which causes the grandparent to change, cascading all the way up to the Merkle root. Any node can detect the tampering by comparing the roots. The hash functions used in blockchains like SHA-256 are cryptographically secure, meaning breaking them would require more computational power than exists on Earth. Merkle trees in Bitcoin architecture. In Bitcoin's architecture, every block header contains the Merkle root of all transactions in that block. The block header is only 80 bytes, but it cryptographically commits to potentially thousands of transactions. Light clients, also called SPV clients, which stands for Simplified Payment Verification, do not download entire blocks. They only download block headers, which is much less data. When a light client needs to verify a transaction, it requests a Merkle proof from a full node, just the sibling hashes along the path to the root. The light client can then verify the transaction belongs to the block without downloading all block data. This makes Bitcoin accessible on mobile devices and low-bandwidth connections. Full nodes verify everything. Every transaction, every signature, and every block. They build and store the complete Merkle tree, but they can provide compact proofs to light clients. The Merkle root in the block header is what gets hashed during the mining process, linking the transactions cryptographically to the proof of work that secures the block. Practical Merkle tree scaling. Let's examine some practical scaling numbers to really understand Merkle tree efficiency. A Bitcoin block with 4,000 transactions has a tree height of 12. Verifying any single transaction requires 12 sibling hashes. That's less than 1 kilobyte of data. Compare that to downloading 4,000 complete transactions, which could be several megabytes. The space savings are enormous. If blocks grew to 10,000 transactions, the tree height only increases to 14, just 2 more hashes needed. For 1 million transactions, you'd need 20 hashes, still less than 2 kilobytes. This logarithmic scaling is what enables blockchain to handle growing transaction volumes without verification costs spiraling out of control. In Ethereum, the situation is similar but more complex. They use Merkle trees which optimize for frequent updates. The principle remains the same: provide compact proofs that don't require downloading everything. This efficiency is fundamental to blockchain's ability to function as a distributed system. Beyond transactions. Other Merkle tree uses. While we have focused on transaction verification, Merkle trees are used throughout blockchain systems. In Bitcoin, there is also a Merkle root for the UTXO set, which is the collection of all unspent outputs. However, this is not included in blocks. Ethereum uses Merkle trees for 3 different trees: transactions, receipts, and state. The state tree includes all account balances and smart contract storage. This allows light clients to verify account balances or storage values with compact proofs. Git, the version control system, uses a similar structure to efficiently track file changes. Certificate transparency logs use Merkle trees to create tamper-proof audit trails of secure sockets layer certificates. Distributed databases like Apache Cassandra use Merkle trees to efficiently detect data inconsistencies across replicas. The pattern is the same everywhere. Organize large datasets in a hash tree to enable efficient verification of individual elements. Any system that needs to prove data membership or integrity without processing everything can benefit from this structure. Common questions and misconceptions. Let's clear up some common questions about Merkle trees. First, do I need to store the entire tree? No, you only need to store the Merkle root. When verification is needed, you calculate the intermediate hashes on demand. Second, can the tree structure change after the block is created? Absolutely not. Once the block is mined, its Merkle root is fixed forever. The tree is immutable. Third, what happens if a transaction is invalid? Invalid transactions are rejected before they enter the mempool. Miners only include valid transactions in blocks, and nodes verify this. An invalid transaction would fail validation long before tree construction. Fourth, can 2 transactions have the same hash? Cryptographically, the probability is so low it's effectively impossible. Hash functions are designed to be collision resistant. Fifth, why not just hash all transactions together directly? That would work for commitment but wouldn't provide efficient proofs. The tree structure enables logarithmic verification. Merkle trees are elegant precisely because they balance compact commitment with efficient proof generation. Conclusion and key takeaways. Let's recap the key points about Merkle trees. They are hierarchical data structures that organize transactions through cryptographic hashing. Starting from leaf transactions, pairs are hashed together repeatedly until a single root hash remains. This root cryptographically represents all transactions below it. To verify a transaction, you only need sibling hashes along the path to the root, which is typically logarithmic in the number of transactions. This makes verification incredibly efficient even for large blocks. The tree structure is deterministic based on transaction order, making it tamper-proof. Any modification to transactions or their order changes the Merkle root. Merkle trees solve the fundamental problem of efficient verification in distributed systems. They enable light clients to verify transactions without downloading full blocks. They are used extensively in Bitcoin, Ethereum, and many other systems beyond blockchain. Understanding Merkle trees is essential to understanding how blockchains achieve security, efficiency, and decentralization simultaneously. They are a perfect example of elegant computer science solving real-world distributed systems challenges. Thank you for your attendance. Please consider subscribing to the channel.